How big is a cloud? It turns out that what we mean by bigness depends on dimension. Are clouds 3D? Or if big enough and flat enough, maybe 1,000 kilometers long, are they 2D? Or are they in between? There's a similar question. How long does the weather last? This question must be answered in order to better know how hot it will get due to the greenhouse gases and other human environmental impacts. To warm you up about size and bigness, can you answer this question? Which of these clouds is bigger? Certainly, if there was a familiar object with a known size, such as an airplane, the answer would be obvious. My journey began back in 1977 during my PhD thesis, The Remote Sensing of Rain. At the time, I was using data from the McGill weather radar that generated rain maps like the ones seen on the right. This was before days of high-resolution computer screens, and instead of pretty colors, numbers and letters were used to indicate the rain rates. My task was to use geostationary satellite data at the left to effectively extend the radar range from 200 kilometers to all of eastern Canada. Interpreting the radar signal itself was not trivial since, as shown on the upper right, each 1 kilometer radar pulse itself contains lots of structures. Overall, this slide shows structures within structures, spanning the range of about 1 meter to the size of the planet. So, how do we handle this huge range of scales with structures within structures within structures? We're used to the idea that as we zoom in, we find something different. This powers of 10, or scale-bound view, is shown here. Every time we zoom into the ladybug by a further factor of 10, we see something quite different, requiring new theories, new models, new understandings. This scale-bound view is so ingrained that it seems obvious. But is it? What happens if we zoom into clouds? Does the fundamental nature of clouds change every factor of 10 or so? Just as I started grappling with rain and cloud structures within structures within structures, this book by Benoit Mandelbrot appeared. It presented a whole theory about them, fractals. Right on the cover of the book, there's this fractal set. If you zoom into part of it, you get another part. This is the property of self-similarity. The small part is the same as the larger part. Thanks to Mandelbrot's inspiration, I failed my PhD. While the scale-bound powers of 10 idea is often true, it doesn't have to be. Here, Mandelbrot is shown looking through a microscope, appropriately, at the Mandelbrot set named in his honor. He's looking into a tiny bit of it down here. When you blow it up, lo and behold, you get something that resembles what he started with. So, the scaling or fractal view proposed by Mandelbrot says that it is entirely possible to zoom in by a huge amount and get something that's actually not new, not different, basically the same. This is what a self-similar cloud looks like. As we zoom into it, although we don't see exactly identical patterns, the cloud-like appearance doesn't change. Are real clouds scaling or scale-bound? Are big and small clouds or other atmospheric structures fundamentally the same, or are they different? There are many ways to answer this. In my thesis, I took images like this one and traced the cloud outline, including the holes inside, to measure the total length of the cloud's perimeter. I then plotted the perimeter length against the scale, estimated by the cloud diameter. When I applied this to many clouds, I found that the perimeter increases the length of the diameter to the power d. D is the fractal dimension. Here, it's 1.35, so the tortuous perimeter of this cloud lies in between the dimension of a straight line 1 and a plane 2. It's actually 1.35, and it's fractals all the way. This beautiful result contradicted prevailing scale-bound prejudices. It so offended the external examiner of my thesis that he failed it. To satisfy him, I had to remove the fractal half of the material, including this result, and resubmit the thesis. Once the revised, amputated thesis was officially accepted, I published the results in the journal Science, giving my career a big boost. So what is the fractal dimension? We're used to the idea the area of a square is the length of its side raised to the second power. The volume of a cube is the length of the third power. The general relation is shown here. In the example I just gave, the size is the perimeter length, the scale is the diameter, and the cloud and the dimension is 1.35. The problem with the perimeter length relation is that it spans clouds 1 kilometer across to over 1,000 kilometers long. However, when you view the Earth from outer space, the atmosphere appears like a thin onion skin only about 10 kilometers thick, 1,000 times smaller than the Earth. How is it that we still get fractals all the way? Even if we admit that clouds are fractals, to many it seems obvious that there must be at least two types of fractal clouds. Small, roundish fractal clouds that would tend to fill a sphere, and large, thin, disc-like fractal clouds with the transition from one type of fractal to another occurring at about 10 kilometers, the atmosphere's thickness. Shouldn't average small clouds be three-dimensional and average large clouds be two-dimensional? So, how did nature solve the onion skin problem, allowing for fractals all the way? This is a vertical section taken from the CloudSat satellite showing a vertical section of just one cloud. This cloud doesn't really look either like a 3D sphere or a completely flat 2D disk. You can already see that the large structures are flatter, whereas the smaller ones show filamentary vertically oriented structures. Turns out that when you do analyze the data systematically, you find that as you go from small to large, the ratio of horizontal extent to vertical thickness constantly increases. The vertical cloud extent varies roughly as the square root of the horizontal extent. This would give a dimension of 2 plus a half is 2.5, whereas the actual dimension is a little larger, 23 over 9 or 2.55. This zoom sequence into a vertical cross-section of the atmosphere shows what this fractals all the way looks like as we zoom in. To make this simulation, I blow up and squash, blow up and squash, blow up and squash. Contrary to the self-similar simulation that I showed earlier, even though the shapes change as I zoom, it's still fractals all the way. When I did my thesis, and for many years afterwards, I thought that my finding that it was fractals all the way would force scientists to change the way they model and forecast the weather. However, by the 2000s, it became clear that weather models had become pretty good, with predictions having some skill a week or more ahead. Beyond that, the skill decreases rapidly since prediction errors caused by tiny perturbations, famously the flapping of a butterfly's wings, becomes huge. Later, with my colleague Daniel Schertzer, we found that the weather models had fractals all the way implicitly built into their equations, helping to explain why the forecast could be so good. But even if weather models were good at improving, there were problems brewing when it came to the climate. We urgently need climate models to figure out how hot it will get in the year 2100 and how to find different strategies of reducing CO2 emissions and how they may play out over the next decades. Today's climate models are souped-up weather models. To project the climate to the year 2100, they forecast the weather every hour until 2100. This might include a snowstorm in Montreal at 9 a.m. on December the 13th, 2099. Although it is known that this precise forecast has zero skill, it is nevertheless hoped that by averaging the forecast over the decade from 2090 to 2100, that the average temperature increase will be accurate. To gain confidence, to determine their uncertainties, the forecast of many models are compared, and the spread between the models, the difference between their forecasts, determines the overall uncertainty. Probably the single most important characteristic number quantifying the warming is the amount of the temperature would rise if we double the CO2 concentration. Starting with the first climate model in 1979 right through 2021, climate models have predicted that such a doubling will yield a warming of anywhere between 1.5 and 4.5 degrees C. This 3 degrees C uncertainty range is large, too large, and remarkably, it didn't change for over 40 years. In 2021, the Intergovernmental Panel on Climate Change published its 6th assessment report. The hope was that the 30 or so models that were used would finally reduce the uncertainty to much smaller levels that policymakers need. In the event, the report showed that the models were more different from each other than ever before. For the first time, the overall uncertainty increased to the range of 3.5 degrees C. If this increased uncertainty wasn't bad enough, at the same time, the experts dramatically halved their uncertainty range to only 1.5 C. Effectively, the experts now know better than the models. The experts are needed more than ever. I promised at the beginning that I would explain how zooming can help understand and model the climate. What do we find when we zoom in time? Is it fractals all the way from centuries down to minutes or even seconds, or are there different fractals involved? At the top, we see the temperature in Montreal every month for 50 years. At the bottom, we see it every minute for a day. They are indeed totally different. At scales of 10 days and longer, the temperature shows fractal structures called macro weather, whereas the shorter scales are weather fractals. The difference between macro weather and weather fractals can also be seen in these zoom sequences. In macro weather fractals, we see that successive temperature fluctuations tend to cancel each other out. In the weather fractals, the temperature seems to wander around without fixed value. They're qualitatively quite different. It isn't hard to understand the reason. Cloud systems the size of the planet only live for about 10 days, so macroweather tells us about the succession of planetary-sized weather systems that are needed to model the climate. In contrast, below 10 days at any given point, the weather mostly blows past. Up to 10 days, the temperature record reflects the structure of a single weather system, the details of which are mostly irrelevant for global warming. Mainstream climate models start in the weather regime and forecast the weather hourly to 2100, only to average most of it out to get a 10-year temperature estimate. The averaging confirms that most of the details are irrelevant. The alternative is to exploit the different macro-weather fractality and to directly construct macro-weather models starting at monthly resolutions. At the same time as the sixth assessment report came out, my colleagues and I made climate projections based on such macro-weather models. These projections reduced the uncertainties from a range of 3.5 degrees C to less than 1 degree. Since the new macro-weather model avoided calculations of irrelevant data, the projections were made on laptops, not computers. For a long time, it seemed that understanding the fractal nature of the atmosphere was just a mathematical curiosity, perhaps helpful for understanding the weather, but no more. Yet, as frequently happens in science, fundamental insights eventually do have consequences. The seed planted 40 years ago that clouds are fractals all the way has finally given way to new ways of more accurately projecting the future of our warming planet. So, next time you go out for a walk, look above and admire the structures within structures in the clouds, and then the beautiful fractal landscapes below.